kind of like warm-ups in terms of things that we already know about probability that are obvious to us. And we're going to work into things that may not be quite as obvious. I'm going to open up the first file, which is called coin toss. And in fact, it doesn't actually start with a coin toss. It starts with something else. Obviously, I move things around now. Okay, and that file, it's visible behind me. Yep, it is. Okay, I'm going to blow it up a little bit so we can see a little bit better. Okay, that file, file starts out giving you a population where the probability that a person is insured is 80%. Okay, so you choose one person randomly from that population. What's the probability that they're insured? 80%, right? 80% of the time, you will be picking someone. If it's truly random, you'll be picking someone that is insured. What's the probability that they're uninsured if you pick one random person? 20%, right? Pretty obvious, right? Okay, now let's take a look at this from another perspective. Let's say you choose 3 people randomly from that population. What's the probability that all 3 are insured? 80% that one is insured? Well, once we pick that one person and they're insured, well, that's an independent event. The next person's an independent event. It has nothing to do with whether the first person was insured, so that's 80% also. And the next person is 80% also, not dependent on what the result of the first 2 picks are. So it's 0.8 times 0.8 times 0.8, right? 0.64 times 0.8. What does that wind up being? About 50% or something like that by the time we're done? Right? You can multiply that out for yourself, right? So the probability that all 3 are insured is the product, 0.8 times 0.8 times 0.8. That's pretty simple because they're independent events. It's all the same outcome. You can look at a coin toss the same way, right? What's the probability we get heads on the first toss? Well, it's going to be 50%. What's the probability that we get, given that we've gotten heads on the first toss, given that the next toss is again an independent event, not influenced, the coin doesn't remember what it was before, we flip it again, it's also 50%. And we flip it a third time, probability on that third try is also 50%. So the probability that if we start from scratch and flip 3 coins quickly, and we look at it, the probability they'll all be heads is going to be 0.5 times 0.5 times 0.5. Same thing for tails. Probability they're all going to be tails is 0.5 times 0.5 times 0.5. We're going to get a closer look at that in a little while when we start. It gets a little bit more complicated when we start talking about what's the probability that 2 out of 3 coins, if we flip 3 coins, is our heads, or 1 out of 3 is heads, and 2 out of 3 are tails, and so on and so forth. Well, in that case, we wind up being in a situation where there's many more possibilities. In other words, a lot of ways in 3 coin tosses to get 2 heads. You can have heads, heads, tails. You can have tails, heads, heads. You can have head, tails, heads, and so on, right? There's several ways for that outcome to occur, unlike when we were talking about all of them being the same, right? So that gets, we're going to take a look at that. We're going to do something called probability trees in a second. Okay, so you choose 3 people randomly. Okay, you choose 10 people randomly from the population. What's the probability? All of them are insured. All of them are insured. Well, as big a sample as that is, it's the same principle. It's going to be 0.8 times 0.8 times 0.8 times 0.8, 10 times, or 0.8 to the 10th power. Okay, so any way we apply this, if it's independent events and they're all either insured or not insured, then we're just going to multiply the probability by the sample size. Okay, number times sample size, so to the power of the sample size. What's the probability we choose 2 people randomly from the population and neither is insured? What's that? I'm sorry, I didn't hear you. Right, 0.2 times 0.2, right? Probability first person's not uninsured, 0.2 independent event times 0.2. Okay, good. Okay. Now, let's say, for instance, that, and this occurs because they're independent events. One's not influenced by the other. In other words, you pick one person, the next person, having picked one person, and they're insured, it's a big enough population that when we pick the second person, you know, that selection is independent of the result we got in the first one. Now, let's think about this. Before we said, what's the probability of getting 3 people that are insured. That was 0.8 times 0.8 times 0.8. Anybody figured that out on a calculator? What was it? Yeah, about 50%, 51%, right? 0.51. Let's say that you did that 1,000 times. You took 3 people, right? And you looked at how many of them were insured. Took another 3 random people, how many of them were insured. Took another 3 people, looked at how many of them were insured. Did it 1,000 times, and you found that 75% of the time, all 3 people were insured. How often did you expect that to occur? No, we expected 1 person. How often did you expect to get all 3 people insured from that population? 51% of the time. You did it in practice, it turned out to be 75%. What does that tell you about that population, about the sample you took? It's not. Remember it had to be independent, right? Each selection had to be independent. This wasn't independent. Let's your selection turns out if that doesn't multiply out and give you the same thing when you sample over and over again, there must be a reason for it. Most likely it's because it's not independent. What would make something like this not independent? Well, maybe some of this population is married couples, right? So 80% of the people are insured, but maybe, there's spouses involved that we counted a different way. And because one spouse is insured, the other one, the kids are insured. So for some reason, it wasn't really independent events, right? So on a test, you might, if you wanted to test whether something was an independent event or not, you might look at that. You might give it that test to see, well, if the outcome, the average outcome, or the outcome that you actually see doesn't match the one you would expect from an independent event. Well, maybe it's not really an independent event, or maybe the selection's not really random, right? Something's wrong there. Okay, let's go back to our coin tosses now. Now, we're going to toss that coin 3 times in succession. And remember before we were starting to examine, well, it's easy to know what's going to happen. It's easy to figure what's going to happen if we're looking for all 3 heads or all 3 tails, right? 0.5 times 0.5 times 0.5. But we want to see the other outcomes. So I'm going to take a piece of paper, and you guys can do this with me if you want, if you have paper handy. And I'm going to draw a tree. Okay, let me see. Oops, I got to plug this thing in. It helps. You guys ever notice that? I swear that when you put in a USB plug, 80% of the time you're putting it in the wrong way, even though it's somehow or other it's not an independent event. I know because I almost always plug it in the wrong way. And now there's finally starting to come out with ones that are reversible. You don't have to worry about the direction. I think I did it again, wrong way. I did it twice, 3 times. Okay. There's our problem here. Okay, that one should work. Okay. Upside down. Okay. Here's some noise. So let's shuffle. Maybe it's being carried by the desk. Okay, let's see. Let me see the sound. Oh, see if we got any guests here. We got a bunch of people logged on. Oh, I know what it is. I'm hearing somebody else's microphone that might be at home, so I'm muting everybody. Good. That's what that shuffling around was. Could have been worse, right? God only knows what we would have heard in the background. So that's the other thing you remind me about. If you don't remember to mute, you can mute your own. Remember to mute your own microphone, and warn me to mute everybody's microphone, so we don't have any embarrassing background chatter. Okay. So at any rate, okay. So we're talking about the probability of coin tosses. So I'm going to start out with, well, we're going to toss a coin. There's 2 possibilities that we have, right? It could be heads or it could be tails. So I'm going to start from this point, and the first toss could be heads or could be tails. Probability is heads is 0.5. Probability is tails is 0.5. So now once we've tossed a head, the next possibility is could be either heads or tails. Probability of getting a second head now is 0.5, given that's already occurred. Probability we get a tail now is down here, and the probability that we get, if first one was a tail, probability we get a head is going to be 0.5, and the probability we get a tail is going to be 0.5. Now for the third coin toss, well, we got to look at every one of these probabilities. In the situation where we got two heads in a row, well, now this is third toss is an independent event, so the probability is 0.5 we get another head, and 0.5 we get a tail. So the probability that we got a head and a tail, again, 0.5 heads, 0.5 tail. And I'm running out of room here, so I'm going to move down a little bit. This next one really is up there. Okay, probability we get a head, 0.5, tail, 0.5, and then finally tail. Probability we get another tail is 0.5. Probability we get a head after that is 0.5. So what's the probability for all these different events? Well, probability that we get three heads is going to be 0.5 times 0.5 times 0.5, which is equal to 0.125. That's 1 over 8. 1/8. That's 1/2 times 1/2 times 1/2 is 1/8 or 0.125. Okay, so it's the probability we get a head, and a tail. Also 0.125. Right? With coin tosses, it's easy because all of these outcomes are going to be multiplied by the same thing. How about heads, tails, heads? That's 0.125. And heads, tail, tail is 0.125. Tail, heads, heads is 0.125. Tail, head, tail is 0.125. Tail, tail, head is 0.125. And tail, 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 0.125. All of these have equal probability outcomes. Well, let's take a look at this. This first one represents how many heads? 3 heads. Second one is 2 heads. Third one is head, tail, head. Head, tail. Well, it's head, tail, and this one is head, tail, head, right? So that's 2 heads. Head, tail, tail is 1 head. Okay, let's go to tails. Tail, head, head is 2 heads. I didn't draw this very neatly, did I? Tail, head, tail is 1 head. Tail, tail, head is 1 head. Tail, tail, tail is no heads, right? Okay, so how many of these represent the outcome where I get 2 heads? I got 2 there, I got 1 there. So 3 out of these 8 possibilities are situations where I'm going to get 2 heads out of 3. Okay, so what is 3/8? That's 0.375. Or in other words, the sum of the probability of this outcome, all the outcomes that satisfy what we were looking for. Okay, what do you think I would get if I added up all these probabilities? 1, because this represents every possible outcome, right? So we're going to move on from there. We're going to take a look at another one of these things. Now we'll notice that the probability of 3 tails, that only occurs one way, when I get 0 heads. So that's only 1 over 8 or 0.125. Probability of getting 3 heads is 0.125. It's the only time it occurs, right? And so on and so forth. What's the probability of getting 2 tails? Well, it's basically the same thing, right? It's the same thing as getting 2 heads, getting 2 tails. It's going to be the same probability. In fact, if you add them up, that basically getting 2 tails is the same thing as getting 1 head out of the 3 tosses. So there's three possible outcomes that satisfy that. Okay, so that's pretty interesting, right? It's pretty simple. So let's move on and take a look at this. We drew our probability tree. Let's look in the next document. Okay, this one, we're going to take that probability tree and we're going to crank it up a little bit. We're going to make it a little bit more complicated. Okay, Students are randomly, they take a test, a multiple, as we used to call it, multiple guess test. Okay, and this multiple guess test has the options A through E. So it's got 5 options. Only one of them is a correct answer. Okay, so what's the probability that they're going to, what's the probability to get any one question right if they don't have any idea, any clue what the correct answer is? What's the probability that they'll guess and get one of them right? Right? 20, right? It's 20%, right? 1 out of 5. So probability of getting any of these right if they have no prior knowledge is going to be 20%. What's the probability they're going to get all 3 correct if they have no idea what the answer is? Point 2 times point 2 times point 2, which is 0.04 times point 2, which is 0.008, right? Am I right about that? I think I am. Okay, good. What's the probability that they'll get 2 or more correct? Uh-oh. We just wound up in this with the same problem that we had with the toy course, didn't we? Right? Except this time we have many more possibilities. That would now this time our possibilities are not all zero point 0.5, right? The probability of getting it right is 0.2. Probability of getting it wrong is 0.8. So it's not a balanced probability anymore. However, we can still draw a probability tree. Well, I'm going to make it a little bit more challenging. Actually, let's do that. Rather than jump right into the next one, let's go ahead and do that. I think it might be worth taking a look at that. Let me see if I can't get back to my page here. Okay, and I hope you guys are giving this a try alongside of me, okay? I mean, it is a lab, right? Not a lecture. Okay, so now what did we say the probability of getting a right answer is? Probability of a correct answer is 0.2. Probability of an incorrect answer, I'll call that C with a little prime next to it, is going to be 0.8, right? Right, so those add up to 1. Okay, so now I'm going to start off on the first question. Okay, I have no idea if I'm going to answer this question right. So there's 2 possibilities. I might get it correct and I might get it incorrect. What's the probability I'm going to get it correct? 0.2. Probability I'm going to get it incorrect is 0.8. Okay, so now that I've taken the first question, they're independent events. I really didn't study for this test, so I have no clue on any of these questions. The next one, I'm going to say, okay, well, chances are I'm going to get the next one correct is going to be 0.2 again, and incorrect is going to be 0.8 again. And also down here, 0.2 correct, 0.8 incorrect. And again, correct. I might get the next question correct or incorrect. Chances are 0.2, 0.8, and this is going to be 0.2, 0.8 for correct and incorrect. And this is going to be 0.2 and 0.8, correct and incorrect. And finally, the last one, 0.2 and 0.8, correct and incorrect. Okay, so now let's figure out what the probabilities are here. The probability you're going to get all 3 correct, we already said it's 0.2 times 0.2 times 0.2, it's going to be 0.08, 0.008, right? A little less than 1% chance they're going to get all 3 of them correct. Well, what's the probability that they're going to get all 3 incorrect? 0.8 times 0.8 times 0.8. And what was that again? We just did that before, right? 0.51 equals 0.5, okay, 0.52? 0.512. Okay, so let's go through the rest of these. Now, the probability to get the first 2 right and the third one incorrect, 0.2 times 0.2 times 0.8, 0.032. Correct, incorrect, correct is what? Good. Correct, incorrect, incorrect. That's 0.2 times 0.8 times 0.8. 0.64 times 0.2 is 0.3. What was it? 0.18. Okay. And from here, I'm going to get a little bit. No, I'm not going to get 0.8 times incorrect, correct is going to be 0.8 times 0.2 times 0.2 is what? Okay, 0.8 times 0.2 times 0.8. What was that? 0.128 again? Okay. 0.8 times 0.8 times 0.2. That sounds like a repeat, right? Okay. And let's see, 0.8 times 0.8 times, we already did that, 0.512. What should these all add up to again? Okay, they should they should all add up to 1. So what's the probability that we would get 2 correct answers out of these 3? Okay, 2. Well, did I say 2 or more? Mm-hmm. Oh, the question says 2 or more. Okay. Well, what's the probability? Let's for starters say, what's the probability of getting 2 or more? Just 2, right? Probability. Where is the likelihood we're going to get 2? Let's see. Where does that occur? Correct, incorrect. This one satisfies this. Correct, incorrect, correct. This one satisfies it. Let's see. Incorrect, correct. This one satisfies it. Incorrect and correct. That's it, right? Just those 3. Those are the only 3 that satisfy it. So it's 0.096, it looks like. That look right? Okay. And what if it were 2 or more? Right? Well, there's only one possibility of getting more than 2 correct. That's 3 correct. And the probability of it occurring is 0.008. So I just have to add that one to it. And I found the probability of getting 2 or more of these answers correct if I had no idea what the real answers were. Yes. Well, you wouldn't multiply because they're all they sum up to 1. These are all the possible outcomes, right? So you wouldn't want to multiply them. You want to add them. They're all additive. They're going to represent all of the possible outcomes, right? So you're just looking for the particular ones that are outcomes that satisfy what you're looking for. Okay, let me ask you this. What's the probability that I know a student got at least 2 right? What's the probability that that student got all 3 right? Well, I'm only looking at the likelihood, I'm only looking at the probabilities that he got at least 2 right. How many did he get? What was the probability of getting at least 2 right, 2 or more? It was 0.096, it was 0.104, right? That's the probability of getting 2 or more right. Well, given that he told me that, I got at least 2 right, I'm sure of it. But I don't know, I have no idea on the third question. What's the probability that he got all 3 right? Well, we already know that the probability that he got that he got 2 or more right is 0.104. What's the probability that he got that third one right as well, given that he already has gotten 2 right? Well, now we're not really concerned about any of these other possibilities. We're only concerned about the probability he got all 3 right, and the probabilities of getting 2 or more right. So the probability now that given that he got 2 correct, what's the probability that he got 3 correct, given that he got 2 correct? Okay, this is kind of like a wacky form of a conditional probability, right? The condition is that given that he has at least 2 right, what's the probability he actually got 3 right? Well, there's the probability he got at least 2 right is 0.104, right? And the probability that he got that third one right is 0.08, 0.008, right? So given that probability that he that given that we know he got at least 2 right, what's the probability that he got 3 right? Well, it's going to be 0.008 divided by 0.104. And what does that come out to? That comes out to, what does it come out to? 0.077. Okay. Now, let's take a close look at this. If I had asked you in the beginning, what's the probability that he got all three right? What would you have said? Right. Now that I've given you the condition that he got at least two of them right, so what's the probability now that he got all three right? That turns out to be much more likely, doesn't it? 0.077. That's the effect of that conditional probability. It changes, given that you have more information, it changes the probability of the outcome that you're looking for. Okay? That's conditional probability. That's really kind of what this is all about. Okay? Everybody getting pretty comfortable with that? This idea of conditional probability? Yes. No, well, where include two or more includes the probability you got all three. So that's a total probability, right? Remember, the probability that he got all three right, given that he got two or more. Correct. Okay, so that two or more includes that third possibility. Okay, so this sounds interesting. Now, let me ask you something else aside from this. Let's see. How many people do you guys think you would need in a classroom or an auditorium to make it 50% likely that two people would have the same birthday? Okay. How many of you think there's 365 days, right? So we're looking for the probability that two or more people would have the same birthday within that group that's in that auditorium. Would you say you need more than 100 people? How many people think you need more than 100 people? How many people think you need more than 50 people? How many people think you need more than 30 people? This is a tough crowd. Okay, well, obviously you've thought this through a little bit, or you've heard this before, right? Well, your initial assumption would be you need quite a few people. But in fact, if you have two people in a room, then the chances of them having the same birthday are 1 in 365, right? One person has a birthday, that's fixed. Second person, only 1 in 365 chances that person has the same birthday. Now, if you add another person, well, now it's not only is it 2 in 365, but now that other person has two people that he can match a birthday with. So as you increase the number of people, number of birthdays, it gets much more likely, right? So I think it's actually about 32. Levi, do you remember? It was about 32 people or 30 people or something like that. Yeah, to have a 50% chance. I think you have to do. I think it's no, I don't think it's that small. But at any rate. Oh, okay. Yeah, that's cheating a little bit. Yeah. Okay. Any questions on this so far? Yes. I made that up. That was based on the fact that it was a multiple choice question, and there were 5 choices. So if you absolutely know nothing about the question, your chances are 20%, 1 in 5, right? And the 80% is the chances you're going to get it wrong, which is 80%. 4 out of 5 times you're going to get it wrong.
Why did you divide?
The last problem, was a conditional probability, and what the condition was that I knew that he got at least 2 right? So now I narrowed it down to only about 10% of the possible outcomes. In other words, only 10% of the time do we have situations, is there outcomes where you get two or more right? So I'm only interested because I know that's already occurred. I know he told me I got 2 right. I know that's already occurred. He doesn't know if he got the third one right? I know he's already gotten 2 right. So I'm only interested in that group of probabilities because that's already occurred, right? I'm not interested in situations where he only gets 1 right or none right. I'm only interested in ones where he gets 2 or more right. So that's only 10% of that entire universe of outcomes. And of that, the probability that he gets one, and within, as we started, probably within that he gets one, all three right is only 8%, is only 0.8%, 0.008. So the probability, given that the other part occurred, I'm only interested in that 10%. So it's basically 1% out of 10% is the probability that he would have three right. Now that I know that I'm only dealing not with all of those possibilities, but only a small portion of it. So I wind up being in the range, being close to 10% instead of like that 1%, where we were starting from scratch and had no information. Okay, sometimes you start explaining this over and over again, and if you talk long enough, it makes it less clear. So, I mean, I think that's the nature of the beast of this stuff sometimes. Okay, so I'm gonna close that. Gonna move on to the next thing. No, maybe I'm not. Yeah. Now, I think this might make this idea of conditional probability a little bit clear. I'm trying to attack this from a number of different angles. So this idea of conditional probability gets maybe a little bit clearer when you see it from different angles. Okay, so now here's the table. This table represents the marital status of the U.S. population, 18 years and older, and these numbers represent millions. So in the rows, we have gender, male and female, and in the columns, we have marital status. So if I asked you how many males in the U.S. population are married, 104.9 million, right? How many females in the population are married? Okay, if I randomly choose one person from this population, right? From this, I'm sure I misspoke. What percentage? I meant to say what percentage of the population is male? How many people in this population are male? It's 104.9. How many people in this population are female? It's 109. I told you that's what happens. You keep talking about this stuff, it gets worse. How many people in this population are female? 109. If I take a single person, if I randomly select a single person from this population, what's the probability that they're male? Don't give me the actual percentage, but tell me what the ratio would be. Over 214. So right. So you guys, 104.9 over 214, 214.2 million. Okay. Let's see. What's the probability that you randomly select a person and that they're divorced? Okay, well, let's think about that. So 21.7, I heard, over 214, right? So 21.7 is there's 21.7 million people divorced out of the population of 214. That's your probability of that individual you picked out there would be divorced. What's the probability the person is male? We just did that. What's the probability that a person is both male and a widower? And let's say you randomly pick one person in this population. What's the probability they're both male and a widower? 2.7 over 214.2, right? Everybody agree on that? Okay. Okay. Last one. This is the punchline here. Given that a person is male, what's the probability that he's married? Okay. Given that a person is male, there's 104.9 million people that are male, and of those 104.9 people, right, 63.5 million of them are married. So given that they're male, so that eliminates all these other possibilities. We forget about everything but the people in that row, right, that male row, and we see 63.5 million out of 104.9 million. You can make up a million of these conditional probabilities. Given that a person is widowed, what's the probability that they're male? Oh, hang on a second. 2.7 out of. Okay, good. All right. Okay, good. So we got another look at that conditional probability. This time we're dealing with the real numbers of people. We're actually counting people. Before we were dealing with probabilities, right? The probability of this particular outcome, the probability of this, and we were examining all the probabilities for all the different outcomes. Okay, so now we're really going to get into using this usefully. We're not going to go into part four. Part four is a lab that Ali put together that maybe at some point we'll go over online because I want to move into diagnostic testing. And basically, he's taking a population like the example we just had before, and he's really dissecting it. And he's using mathematical notation for the probabilities and maybe something that is good to go through because you'll get a little bit more used to using the correct notation. Okay, but I'm gonna pass on that for now. Maybe we'll get together during the week sometime this week or next week, and we'll go over it online between classes. So I'm going to go up to number 5, diagnostic tests. Okay, so before we actually examine this population, we know that a sample of a group of 100 subjects that are known, someone developed, anybody here allergic to nickel? In other words, you wear a stainless steel, like a watch strap or something like that, you get a rash, or earrings or something like that. Anybody here? Because I'm surprised because I can't wear a watch because the back of the watch I get a rash underneath it. I don't know why it happened. I always thought your immune system got less prone to allergies as you got older. In fact, it's not. It's the other way around. I guess because you've been exposed more frequently and stuff like that. But that's what my doctor tells me anyway. So at any rate, so I'm slightly allergic to nickel. I get a rash. And nickel allergies are on the increase. I think it's almost the prevalence might be 5% or something like that now of the population. One of the reasons why the incidence is going up is because what do you call it? No, not fillings. I mean, piercings are so popular, and a lot of piercings are like stainless, right? Or have nickel in them. The alloys have, yeah. I don't think they use. Yeah, they might use nickel in. Yeah, I'm not so. Yeah, but these are in contact with your skin and stuff like that. A lot of people are becoming sensitized to nickel, right? So that prevalence in nickel sensitivity is going up. That's a good excuse for doing this, right? Maybe not. So I made up a fake population here to make the numbers a little bit more friendly. Okay, so somebody because the prevalence is increasing, there's some interest in the diagnostic test, right? Rather than go to the allergist and do a patch test for a million different things and so on and so forth. A nice simple test for nickel sensitivity would be pretty valuable, right? So